Hey guys, we are on page 5 of your notes, but we're going to do a little bit of background first. This is all about unbiased statistics, but we're going to talk about the difference between some things right now. So, we can have a statistic value, and remember, a statistic is just any value that you get from a sample. So, we could get, means from a sample, we could get standard deviation of a sample, we could get the range of a sample, pretty much anything you want. You can get it from a sample, and that makes it a statistic. Okay? Statistics are either biased or they are unbiased. A biased statistic, what on earth does that mean? So you're going to have some sort of population parameter value. So if we come back here and let's just think of a mean. Okay? You might have a population. Like if we go back to Huntingtown High School, maybe the average age at Huntingtown High School is 16 years old. I have no idea. Okay, I just made that up. That is the population parameter value. Okay, and maybe the population parameter value is 16 years old at Huntingtown. Okay, what would make something biased? That means when you take a sampling distribution, you take a ton of different samples and you take the mean of all of those samples, they should match. So if you take a sampling distribution and you come back with a value of, I don't know, like 19 years old for whatever reason, if these aren't equal, it's biased. Okay? If you take a sampling distribution and you find the mean of all your different possible statistic values and these two things match, then you have an unbiased statistic. We want unbiased statistics because they are a good estimator of the population. Sometimes you might not know the population value, but you have a sampling distribution, and so you're like, oh, I can predict what the population looks like, and that's where we're kind of going with this. Let's just look at an example of that, though, if that was a little bit too foreign. So here is my population that I'm showing you right now. Maybe there's a kids club, and the mean age of all the people that go to that club is 15, okay? And so, like an like a school club or something like that, okay? This is the population, okay? And so if I took a random sample of 4 people from that population, you might find that their mean is 10. Or if I take another sample, you might find that their mean is 25 years old. Or if I take another mean, you might find that the mean is 20. So what happens here is we talked a little bit about sampling distributions, but you take all your different averages of your samples and you plot them. So looking at this, here is one statistic value. I plot that. I look at another sample and I plot that statistic value, and I do another sample and I plot that statistic value, and then here's a whole bunch, all of my different sample means. Okay, these are all the sample means. I know that my population mean is 15. That's right here, right? And we talked about in unit, unit 1 or something like that, way back when, in order to find the mean of, if you were just given the picture and you didn't want to sit here and calculate all the mean of this sampling distribution, one easy way to find that is the balancing point, okay? When you find the place that you have a balance point, or balancing point, whatever, that is your mean. So if I were just to do a quick glance of this, my balancing point would probably somewhere in here, right, to balance that curve. And so it turns out that my sampling distribution is actually kind of in the same spot as my population mean. Do you guys see that? Population mean and sampling distribution mean so happen to kind of be in the same spot. And when that is true, when they are both equal to each other, the sampling distribution and the population mean, we call that unbiased. Okay? So that's kind of the idea of what we're talking about here. And so let's look at some other little examples here on the side. I get it, you're not copying your notes, whatever, it's fine. These are just, you gotta figure this out. So here are 3 different sampling, maybe I should write that up here, sampling distributions. Okay, and so what happens here is they tell me that the population parameter of whatever I'm talking about is 5. So my population thing is somewhere here. My population thing is at 5, and this one is at 5. So when I go to look at this, I now need to find, okay, where would be the balancing point of my sampling distribution. To me, it looks like my balancing point would be somewhere over here, because there's more on this side right now. It would be somewhere in here to balance this curve. So I would say that this one is slightly biased. So this has a slight bias on this one, because the mean of my sampling distribution is right here, right? If I look at this one, where does this curve get balanced? Oh, the mean of my sampling distribution is going to be somewhere over here. Are these in the same spot? Nope, I would say that this one is definitely biased. And then if I look at this one, is the mean of my sampling distribution, where is it balanced? It's probably balanced in here. So the mean of my sampling distribution looks like it equals the mean of my population, or my population parameter, whatever it is. And so this one I would say is unbiased. All right, let's actually jump back to your notes and write some of this stuff down, but hopefully that illustration was a little bit helpful. Okay, where the heck are we? All right, so here is kind of the definition. So, an unbiased statistic. If you took the mean of every possible statistic value, right? You put all of those all those different means, and put them on a sampling distribution. Okay, if the mean of all of those of your sampling distribution equals the parameter, you have an unbiased statistic. Okay, so guys, way back long ago we talked about biased samples. We are not talking about the same thing right now. A biased statistic is different than a biased sample. Okay, and so long story short, this means if we took the mean, and this is kind of worded like strangely, if we took the mean of all possible statistic values. That's what that's trying to say. All possible statistic values. If the mean of all possible statistic values equals the parameter value, you have an unbiased statistic. So that means if we took like ranges, we were looking at ranges, and we know that the range of the population is, I don't know, like 10, and you took all of the different ranges and you found the mean over here, they should be equal if it's unbiased. Now the range was a bad example there, because we're going to see that in a second. So let's look at this. These two things right here are facts, okay? This is a fact, and this is a fact. And we are going to use these facts in the future. So it's good that we get this fact in our brain. So right here, if you were to take the mean of all possible sample means, so we have the mean of the sampling distribution. I'm going to write this out. This is the mean of sampling distribution. So the mean of the sampling distribution equals the mean of the population. Okay? That is a fact. That is just going to happen. This means that the sample mean is always going to be unbiased because it is correct on average. Over here, this is also fact. So this is saying if I took the mean of a sampling distribution for the ranges, if you took the mean of all the different ranges for all your different samples and you found the mean of that, it is actually not going to equal the population range. Okay? The sample range is always biased because it is wrong on average. If I look up here, I might have said this right. This is the mean of the sampling distribution of all the different means. Okay? Let's just practice this one more time. I could show you some of these. This one is always going to be right. If you take a mean of a whole bunch of different things and you take the mean, they're going to end up being around the mean of the big population. If you take the range of a population, it's very spread out all over the place, and then you take the range of a whole bunch of tinier samples, they're just not going to equal each other, okay? Let's look at these. So, down here, we just talked about these are all the different sampling distributions, okay? the sampling distribution, let's find the mean of the sampling distribution. That's where it's going to be balanced. So the mean of my sampling distribution looks like it would be in here. Okay, so that is the mean of all my different statistic values right there. And in here, this looks like this is the balancing point. So this is the mean of all of my different statistic values. And my balancing point in this one, where would this balance? It would probably balance somewhere in here. So this is my mean of all my different statistic values here. Okay? Looking now, I can see clearly that the mean of my sampling distribution does not equal my parameter. And here I can see that the mean of this sampling distribution does not equal my parameter. And this one, oh, they line up. So the mean of this sampling distribution is equal to the parameter value. So when I look at this, I would say that this one looks like it's definitely biased. This one's biased because they're not equal. This one's biased because they're not equal. But this one is unbiased. And let's kind of like, but if you look, this one's pretty close, and this one's much farther away. So I would say that our statistic here has a low bias, because it's pretty close, okay? This one over here, this statistic, I would say this statistic has a high bias, because it really is not that close, okay? This one over here, I would say that our statistic here has no bias. Alright, and so hopefully that this is helpful and we're starting to understand the idea of a biased statistic versus an unbiased statistic.